Hello everyone, my name is Odari kHz and today I'm going to show you how to design a filter using Butterworth, and we are going to do the simulation using Python, then MATLAB, then we are going now to implement the real thing on LTspice. So I hope from this video learn a lot, maybe using Python to do the simulation and also using MATLAB, because you'll find that this similarity on how you call the functions and how you implement the filter. So let's say you have been given a task, you're an engineer given a task that to design a fifth order filter um, response, and you have been given the specifications, maybe the filter specification and the order verification. So maybe you've been given a filter specification. Mostly you're given the passband, edge frequency, the maximum passband attenuation into the passband. You have the stop band edge frequency and the minimum stop band attenuation. So this data, you will use this data using Chebyshev. You can be able to come up with a type of a filter order, come up with the polynomial, the transfer function, right? And be able to maybe now do the scaling, because for the first time we use normalization, because if you use normalization, you can be able to scale to any value that you want. Maybe having a normalized transfer function makes the simulations very easy. Maybe you want to design any kind of a filter of the fifth order of any kind. Maybe you have different values, you can be able to scale them and get the values from that filter order. So as you all know, the Butterworth filter, the first thing is find the order, and the order, this is the formula here. This is the formula that you use to find the order of a filter. From finding the order of a filter, now you can be able to find the poles, because we are using a unity, a frequency of omega is equals to 1. So you have a circle of 1. So given that the n is 5, you can be able to use the formula here. For the pole estimation, you can be able to find the formula, but you know this is an odd number 5, so therefore the first pole will be at 1. Okay, the second pole will be at after 36 degrees, the other one negative 36 degrees, and the conjugate on the other side of the circle. So you can see that this is the angle. They find the 108, 144, 180, 216, 152. All those, they are just the pole positions, of which you can be able even to use a different criteria instead of using that formula. Let's say this is a circle here. Let's assume it's a circle of radius 1, so it's on a Cartesian plane. My drawing, it's on a Cartesian plane, and you said that because it's an odd, you have the value here at 0, and remember it will have its conjugate on the other side. Then because there are 4 values, we'll have the first one here, the second one here, the third one here, the fourth one here, as you can see. So this, from this to this, the angle is 36 degrees. The other one is because we take 180 divided by what? 5. So they'll be separated by 36 degrees. Every pole will be separated by 36 degrees. So you can see that this one, you can be able to find the sine, the cos of 36 degrees plus j sine of 36 degrees, of which, let me confirm on my calculator. If you do cos 36 degrees, you get 0.890. And when you do sine 36 degrees, you get 0.5878, of which I think this pole here corresponds to what? Corresponds to this. Corresponds to this, because we need the conjugate. So we need the value that are on the left, because the system will be stable. But now it has conjugates, so you'll find that this has a conjugate of the other value, this has a conjugate of the other value, and so forth. So you can be able to use a unit circle to do that, but if you use this formula, then it gives you the values easily. So from finding the poles, now you can do the expansion. You take the conjugates, because you see this has a conjugate here. You see this one has its conjugate here. Then this is just at, because you said the first will be at 1, because it's the order is an odd. The order is an odd value. So you see that when you do the conjugate of this, just s squared, you do the expansion of which I think you know that. Then after that, you can do this, then get the real pole and the two poles. So after that, now you take all these, you multiply in the denominator. So you take s plus 1 into this, into that, you get uh, something like this, of which you can be able to get the transfer function. So from getting the transfer function, the next thing is to get what? The now do the scaling, because you see the first part you cascade. This is a first order, you cascade with the second order, you cascade with another order when implementing using the Sallen-Key topology, right? So from that, you're going to component value and verification framework, for which you know that uh, the value of C, you can be able to get the value of capacitor given that maybe you are using R as 10. And remember, I'm using a unit, the unit, it will be unit, the value of R and A can be unit, so I can just have just a connection. So I'll not use resistor R4 and resistor R3. So from that, you can be able to calculate everything from now finding the values, doing what we call scaling. From scaling, you come up with the values of which you'll be using to do the simulation. So these values, you'll use them. Then from that, we go now to LTspice and try to simulate and see what you are getting. Is it what we expect? So let's start from verifying this using MATLAB, maybe verifying this section using MATLAB. So to verify this, let's start with Python first. Let me do this. What I need is this statement only. I can get the simulation. So what this is the notebook. You can find the link is in the description, so you can head to my GitHub. You'll find filter design, get into filter design, then you get this information or even this notebook and try to simulate. So I'm going to install the following library. The first library, I'm going to import numpy as np. I'm going to import, I'm importing what? Scipy as sp from scipy.signal import but order. It's like this or like this. I'll see, I'll check beta. Then from that, can be able to import those libraries. I'm going to import matplotlib.pyplot as plt. I'm going to import warnings because from warnings import filter warnings. Then I'm going to say filter warnings. Yeah, then I'm going to because I'm going to use the control library from MATLAB, and the matlab.tf, it has been deprecated, so I'm going to use ignore so that I ignore those messages. So from this, I'm going to install import control as ct. Then from I'll just import control.matlab as empty thing, as ct. So from that, after installing this, I think I have a beta order. Okay, I'll check, but I think something like, let me check to get the order of the filter. This is a function that is, okay, I'll check. So let me just have this first. Let me check. Signal dot that gives it some time because it's running. Trying to do. Let me check. Something that it's not happening. Okay. Let me refresh it. Let me reload, maybe. Yeah, sometimes it happens. So warnings, can run that. Okay, nice working. Then import .matlab as empty, import controller ct. Then you can import science plots. Then you can say filter. Then then I'm going to configure the style for the plots to look scientific. What's my configuration with latex? Let me have no latex. Yeah, so everything is okay. But I wanted to see I spot butter odd. Yeah, I think it's butter odd. Yeah, butter odd. So this but odd. Yeah, but odd. So from that, now to come up with the order, because we need the order and we need the uh, the frequency. We have to do this butter order. If you don't know, you have to those question mark, then you run that. So it can tell you that we need the pass band frequency, we need the stop band frequency, and all this information they have been given here. We need the attenuation, the band pass, the maximum band attenuation, G pass. Then we need the minimum stop band attenuation, which is the G stop. Then if by default, if you want to design an analog filter, by default it's digital. So you have to have that boolean to true, only that. So those are the information that we're going to see. So that you see that we can have this information somewhere here. So you can say omega p is equals to 2 np dot pi multiplied by 1 e3, that is around 1000. Then ws is equals to 2 multiplied by np dot pi dot multiplied by 2 3. Then we have g pass, or you can just say gp. Gp is equals to 3. Then you have gs is equals to what? Gs is equals to 30.0. Let me have in 0. Then after that, you're going to put those information. So I'm going to have omega p, omega s, gp, gs. Then analog to true. So you can see that you have the filter order as what? As 5. And this is what you got from this. The filter order is 5. So you can see this all calculation. You don't need to do, because if you have such kind of technology currently. So you see that the NP is equal to 62.86, and this is what we got. This is what we got here as 62.83. Somehow close to that. Okay, so from that, now we want to find the numerator coefficients and the denominator coefficients. So the numerator, can call them b, or just you can search b matter. You can see it. Let me have enable scrolling. You see, it will tell you that the parameters that we need is the filter order and the critical frequency. And what it will return is b and a. B is the numerator coefficients and a is the denominator coefficients. And you know that the denominator, when equated to 0, it gives us what we call the port. So from that, I'm going to have b and a, then beta. Then I'm going to have n, because I'm just copying this information here, n. Then the b type, let's design a low pass filter, because the information that provided for a low pass filter. Then you can have the analog to true. analog to true, then run that. So you can see the coefficients of the numerator is that, the coefficient of the denominator is that. And from low pass filter, we know that the coefficient, the numerator coefficient, like the highest order is 0 because it's s raised to 0. So you don't have any coefficients of higher order, maybe s squared, c and something like that. So you can see that this is the transfer function that we are using. The highest just a coefficient. There's no any s or what. So from this now, you have to now come up with a transfer function. So to come up with a transfer function is very simple. I'm going to use now the MATLAB to come up with the transfer function. So I'm going to say the system now is equal to mt dot the transfer function. We need the numerator, which is b, the denominator, which is a. If you don't know that, just have to then can enable scrolling. So you can see that we need the numerator and we need the denominator. So the numerator is b, the denominator is a. Then we can see our what is our system here. So our system is equal to what? So this is our system s raised to 5 because it's a fifth order filter. So the highest order is 5 because you see that's something raised to 5. So this is the transfer function that is scaled, not normalized. When you normalize, we expect that the value of the numerator to be 1. But now this is it has been scaled so that to have the values. So from that, we are going to do this. We are going to get the frequency, like we want to find the value, how the frequency response with difference in frequency. So from that, we have to do what we call we can get the magnitude, the phase, and the omega. Then you can say mt dot board. All these they have been deprecated. I don't know. I see, but the TF has been deprecated because when I run without filtering the warnings, it will tell you that I use the frequency response instead of the TF because it has been deprecated. So from that, I'll have the system. Just wait for a minute. Okay, so you see this, so I can be able to adjust the figure. So plt dot figure fig size. I can have 10 by 6. Let me see, 10 by 6. 10 by 6. Yeah. Then I can be having plt.show. Yep. So you can see that this is the magnitude response and this is the phase response. So you can see there's no oscillations in the passband. It's just flat, maximally flat. So this is now the response. Now, when you simulate an LTspice, we expect to get such kind of a plot. We're getting this simulation here. Now let's go to LTspice and try to simulate and see if we'll get the same plots as that we have got here. So after drawing the board plots, and you can see that the magnitude spectrum, the magnitude frequency spectrum, you can see that it's flat in the passband and start to alternate after the desired frequency. So from that, we can see that these are the values that I'm going to use to draw that, and there's something you call standard values. Every resistor, if you get a resistor of 100, you'll go to the table, look for a standard value. So I've tried to look for standard. So I decided to use all the resistors as 10k ohm. So I've decided the standard is 10. 15.92, you look for a standard that is like close to that. So let me show you. So when you are doing a design, you don't just use any value of the capacitor, unless if you want a different kind of a capacitor, you can be able to put them in series or in parallel to obtain maybe a certain value. Also, this does the resistor. That's why I've been taught how you maybe put resistors together, maybe in parallel or in series, so that to come up with a different value. But that is not standard. Maybe you need 5 ohm, so you can put parallel two resistors, 10k resistors, you can get 5. If you need 20k resistors, so you can put 10k resistors in series. So there's some standard. So you can come and search standard values of capacitors. If there's a table for that. Let me use just this table here for just to show you how. So you can see, let me just a minute. Yeah, let me open in a new tab. So these are the standard values. So I got what? I got this is 15.92. So when I come to this, I can look for 15.92K, 15.92, something close to that. So you see, I'm not being able to find something like, so it's either you find 16, 15, or 16. There's no 15.92. So, but when your project has precision, then you can be able to do what I've told you, put them in parallel, put them series to obtain such kind of capacity. So you find that 15.92 is close to 16. That's why I picked 16. The other one is 19.69, 19.69, 19.69. There's 18, there's 20. 19.69 is close to 20, so I chose 20. There's another value of the capacitor that is 4.91. So 4.91, so 4.9, 4 point something. So there's 4.3, 4.7, 4.9, and there's 5.1. So I opted for 4.7 instead of 5.1. So this is how now you can be able to pick the standard values. This is for the resistors, the same they apply to the capacitors. Uh, so from that, now let's go to LTspice. This is the circuit I've built. You find that this is the first circuit, as you can see from this uh, uh, this stage here. We have only a capacitor and a resistor, and it's in a low pass. So what I've just is just a voltage follower for that. Uh, a voltage follower. So you can see I've just have a voltage follower, it's like a buffer, but a voltage follower. So I have a value of 16 and 10. This is the Sallen-Key configuration here. Then there's another Sallen-Key configuration. So we have cascaded the first one, the second, and the third. And to do the simulation now, let me do away with this. Because you are doing the AC analysis, you want to vary the value of frequency and observe the changes of the magnitude and phase with change in frequency. So to do that, you come to this here, you want to configure, then you come to AC analysis. So there's type of, there's octave, there's decade, the change is times 10 times 10 times 10. There's octave, there's linear, just 1, 2, 3, 4, 5, 6. There's list, but I'll opt for decade. So the number of points per decade, let me have 1,000. You can have any value. Then they said you you choose either decade. If you choose oct, it will be oct. If you choose list, it will be list. If you choose linear, it will be linear, but I've opted for decade. Then they told you to the number of points here, then the start frequency. So the start frequency is, let me start with 1. Then the let me have 1 mega. Okay, so I can have it there. Then the magnitude of this, I'll have it as, you see, so I have a value of 4. But you don't choose any type of the signal type. Just have none, then come to have small signal AC analysis. So I have a value of 4. Or I can have a value of maybe even 0.1, but I've opted for 4. So from that, now I can have, okay. Then this is the positive voltage, the negative, the rail this op amp used as a rail, and this I've used the universal op amp, and these are the you can see that the gain bandwidth is 10 megahertz, the slew rate is 10 mega, limit 25, rail 0. So you can see the input impedance is 500 megahertz. So I'm using that kind of an op amp. So from that, now is to just to simulate. So I can hit the run button. So after hitting the run button, I can get this, but this one is for the plotting. So if you check the input, you can see uh, this is the first plot. The first plot is the magnitude plot. Everything is just constant because a value of 4 has an angle of 0 and a magnitude of 4. Now you change that 4 into now you change that 4 into mega. Like, what am I saying? You change that 4 into dB, and to change that, just simple. I can just type just let me have that value
how these values, so I can have 20, we have 20, then log 4. So I get the value is 12.041. So that's the criteria they use. So you find something like, if you come to add, then I can have the value. So you can see the values 12.0412. So if you look at what you got from this is 12.041. If you round up there, you get to. So this is how they got that. The phase is just 0. You can see it's 0 degrees here, just 0 degrees. If you hover there, you can see 0 degrees. So from that now, you want to simulate. You want to see the output. This is the input. Now we see the output here. So if you want to get the output, then I can, let me do away, then run again. Then from here, I just have to tap here. So you can see this is the magnitude plot. Then this one the phase plot. So let me see if they match with our expectation. Okay, so you can see it's just something that is flat until it reaches maybe our cutoff frequency, something like this is 1k. That was our cutoff frequency. If you have other cursor, yeah, you can see the value is around negative 15.133. So that's around 1 over the square, 0.707. So it's 20 log 0.707. But remember the value is 4. So you just multiply and get that dB, the magnitude. So if you see the angle at that point is equals to negative that, you can be able to do. So this is how you get. So if you look at this plot, the magnitude plot, you can see there's some similarity with our simulation. So you can see just flat until we hit somewhere here at 1 kilohertz. So this is how you can be able to do. So in the next session, I'm going to show you how you can do this using MATLAB, and also because you have already built for the for the LTspice, I just show you how you can be able to use MATLAB and come up with this. So you see, you spend less time doing this because just something easy, something precise. Thank you for watching. Follow for more. Follow and subscribe to my YouTube channel. Thank you.